Hello students, in this video I am going to talk about chapter 5 of Guyton, that is membrane potential and action potential. Take out your highlighters and highlight the important text, and for your exam you just have to read this text, the highlighted text. So let's start. Electrical potential exists across the membrane of virtually all cells of the body. Highlight this line. Some cells, such as nerve and muscle cells, they generate rapidly changing electrochemical impulses at their membrane, and these impulses are used to transmit signals along the nerve or muscle membrane. In other type of cells, such as glandular cell, macrophages, and ciliated cell, local changes in membrane potential also activate many of the cell functions. Just highlight till functions. Then let's come to the next heading, that is the basic physics of membrane potential. And under this, it is written membrane potential caused by ion concentration. Highlight these two headings and differences across a selectively permeable membrane. About figure 5.1a and b, you can just read the figure, mark figure 5.1. If you want to read the text, you can read it, but if you can understand it through the diagram and the slides, it's enough. All right. The next heading, the Nernst equation, describes the relation of diffusion potential to the ion concentration difference across a membrane. No need to read any of the things in it. Just learn the definition of Nernst equation from the slides. The next page, the Goldman equation. We already have discussed in the lecture that the Goldman equation is used to calculate the diffusion potential when the membrane is permeable to several different ions. No need to highlight any of the text in this a heading. All right, just you must know Nernst equation and the Goldman's equation definition only. All right, now next heading is the measuring the membrane potential. The first three lines, the method for measuring the membrane potential is simple in theory but difficult in practice because of the small size of most of the fibers. Highlight this three lines only. Now an important heading is the resting membrane potential of neurons. The resting membrane potential of large nerve fibers when they're not transmitting any nerve signal is about minus 90 millivolt. That is, the potential inside the fiber is 90 millivolts more negative than the potential in the extracellular fluid on the outside of the fiber. Just highlight till here. Then the next heading is the active transport of sodium and potassium ion through the membrane is through the sodium potassium pump. Just highlight this heading. No need to go into detail. You can see the details from the slides. If you cannot understand anything from the slides, then you can read the details, but no need to highlight anything. The next thing is the leakage of the potassium through the nerve cell membrane. No need to highlight anything from here as well. Then there is the next page, origin of the normal resting membrane potential. No need to read about this, the contribution of the potassium diffusion potential, contribution of sodium diffusion. Do not read this, or the contribution to the sodium potassium pump. The details are given in the slides. Just do this page from the slides. Now the next page is the neuron action potential. So let's read from here and highlight. Nerve signals are transmitted by action potential, which are rapid changes in membrane potential that spread rapidly along the nerve fiber membrane. Each action potential begins with a sudden change from the normal resting negative membrane potential to a positive potential and ends with an almost equally rapid change back to negative potential. To conduct a nerve signal, the action potential moves along the nerve fiber until it comes to the fiber ends. Just highlight till here. Then the resting stage. The resting stage is the resting membrane potential before the action potential begins. Highlight this line. The membrane is said to be polarized during this stage because of the minus 90 millivolts negative membrane potential that is present. The next is the depolarization stage. At this time, the membrane suddenly becomes permeable to sodium ion, allowing tremendous number of positively charged sodium to diffuse to the interior. The normal polarized state of minus 90 is immediately neutralized by the positively charged sodium ions, with the potential rising rapidly in the positive direction, and this process is called depolarization. In large nerve fibers, the great excess of positive sodium ion moving to the inside causes membrane potential to actually overshoot beyond the zero level and become somewhat positive. In some smaller fiber, as well as many CNS neurons, the potential merely approaches the zero level and does not overshoot the positive value. Now, in repolarization, just highlight the fifth line. Rapid diffusion of potassium ion to the exterior re-establish the normal negative resting membrane potential, which is called the repolarization of the membrane. Just highlight these 3 lines from the repolarization stage. The next heading is the voltage-gated sodium and potassium channel. The necessary actor in causing both depolarization and repolarization of the nerve membrane during the action potential is the voltage-gated sodium channel. A voltage-gated potassium channel also play an important role in increasing the rapidity of repolarization of the membrane. These two voltage-gated channels are in addition to the sodium pump and the potassium leaky channels. Do not read anything under the heading activation of the sodium channel, and then there is a heading activation of potassium channel. Do not read this. The voltage-gated potassium channel and its activation. Do not read this. Do not read any of the information that is written on page 66. Now let's come to the next thing. Do not read anything in the box, and do not read summary. Do not read page 67. The next important thing you need to know is this blue box, the role of other ions during the action potential. The heading impermanent negatively charged ion anions inside the nerve axon. Inside the axon are many negatively charged ions that cannot go through the membrane channels. They include the anions of protein molecule and many organic phosphate compound, sulfate compound, because these ions cannot leave the interior of the axon. Any deficit of positive ion inside the membrane leave in excess of these negative anions. Therefore, these negative anions are responsible for the negative charge inside the fiber when there is a net deficit of positively charged potassium ion and other positive ions. The calcium ions highlight all the text for the calcium ion. The membrane of almost all cells of the body have the calcium pump similar to the sodium pump, and calcium serve along with the sodium in some cells to call most of the action potential. Like the sodium pump, the calcium pump transport calcium ion from the interior to the exterior, creating a calcium ion gradient for about 10,000 fold. This process leaves an internal cell concentration of calcium ion of about 10 minus 7 molar in contrast with external concentration of about 10 minus 10 raised to the power 3 molar. In addition, there are voltage gated calcium channel. Because calcium ion concentration is more than 10,000 times greater in the ECF than in the ICF, there is a tremendous diffusion gradient for the flow of calcium into the cell. These channels are permeable to sodium ion and calcium ion, but the permeability to calcium is 1,000-fold greater than to the sodium under normal physiological conditions. When the channel is open in response to stimulus that depolarize the cell membrane, calcium ion flow to the interior of the cells. A major function of the voltage-gated calcium ion channels contribute to the depolarizing phase on the action potential. In some cells, the gating of calcium channel is slow. It requires 10 to 20 times as long for the activation as for sodium channel. For this reason, they are often called slow channels, in contrast to the sodium channels, which are fast channel. Therefore, the opening of calcium channel provide a more sustained depolarization, where the sodium channel play a key role in initiating action potential. Calcium channels are numerous in both cardiac muscle and smooth muscle. In fact, in some type of smooth muscle, the fast sodium channel is hardly present. Therefore, the action potential are caused almost entirely by the activation of the slow calcium channel. Increased probability of the sodium channel when there is deficit of calcium ion. The concentration of calcium ion in the ECF also has a profound effect on the voltage level at which the sodium channels become activated. When there is a deficit of calcium ion, the sodium channel become activated by a small increase of membrane potential from its normal. Therefore, the nerve fiber become highly excitable, sometimes discharging repeatedly without provocation, rather remaining in the resting state. In fact, the calcium ion concentration need to fall only 50% below normal before spontaneous discharge occur in some peripheral nerve, often causing muscle tetany. Muscle tetany is sometimes lethal because of the tetanic contraction of the respiratory muscle. The probable way in which calcium ion affect the sodium channels, these ions appear to bind to the surface of the sodium channel protein molecule. The positive charge of these calcium ion in turn alter the electrical state of the sodium channel protein, thus altering the voltage level required to open the sodium gate. This is all about the ions, and highlight all this which is written on the page number, the blue box is on the page number 68. Highlight all the calcium ions and the negatively charged anion inside the nerve axons. These two things are important. Initiation of the action potential, do not highlight any line that is written on page number 68. Do not read, mark this the threshold for initiation of the action potential. An action potential will not occur until the initial rise in membrane potential is great enough to create the positive feedback. This occurs when the number of sodium ion entering the fiber becomes greater than the number of potassium ion leaving the fiber. I think leaving the fiber, just highlight till here. All right. Now you do not highlight anything in the propagation of the action potential. You can do this from the slides, and then direction of propagation. You can see you can highlight excitable membrane has no single direction of propagation, but the action potential travel in all direction away from the stimulus, even along branches of the nerve fiber, until the entire membrane has become depolarized. Then highlight everything which is written under the heading all or nothing principle. Once an action potential has been elicited at any point on the membrane of a normal fiber, the depolarization process travels over the entire membrane if conditions are right, but it does not travel at all conditions are not right. This principle is called the all or nothing principle and applied to all normal excitable tissues. Occasionally, the action potential reaches a point on the membrane at which it does not generate sufficient voltage to stimulate the next area of the membrane. When this situation occurs, the spread of depolarization stops. Therefore, for continued propagation of an impulse to occur, the ratio of action potential to threshold for excitation must at all times be greater than 1. This greater than 1 requirement is a safety factor for propagation. Highlight all or whole of this paragraph, all or nothing principle. The next heading, that is the re-establishing sodium and potassium ionic gradients after action potential are completed, importance of energy metabolism. So as we all know that the sodium potassium pump is responsible to re-establish the action potential, re-establish when action potential is completed, re-establish the resting membrane potential. To make it more understandable, you can read this paragraph under this heading, but do not highlight anything. You can read it for understanding. The next is the plateau in some action potential. So plateau, we have already talked about this. Do not need to highlight anything. You must know this figure. That is figure 5.18. Highlight this paragraph, the cause of the plateau. The second last paragraph under the heading. The cause of the plateau is a combination of several factors. First, in heart muscle, there are two types of channels that contribute to the depolarization process. The usual voltage activated sodium channel called fast channels, and the L-type calcium channel, which is slow to open and therefore called slow channel. Opening of fast channel causes spike push on the action potential, whereas the prolonged opening on the slow calcium sodium channel mainly allow calcium ion to enter the fiber, which is largely responsible for the plateau portion of the action potential. A second factor that may be partly responsible for the plateau is that the voltage gated potassium channels are slow to open, often not opening much until the end of the plateau. This factor delays the return of membrane potential towards normal negative value. The plateau ends when the calcium sodium channel closes and the permeability to potassium ion increases. Highlight these two paragraphs. This is important. Next paragraph, the rhythmicity of some excitable tissues, that is the repetitive discharge. Repetitive self-induced discharges occur normally in the heart, in smooth muscle, and many of the neurons of the central nervous system. Highlight these three lines. Highlight this heading, the re-excitation process is necessary for spontaneous rhythmicity. Just highlight this black heading. No need to read the underlying paragraph. Now the next heading, the spatial characteristic of signal transmission in nerve trunks. We've already talked about this in the slides, but for your understanding, you can read this paragraph. It's easy. If you do not understand anything in it, then you can ask me. So now last page, I guess. So this is the saltatory conduction. Highlight this, the heading, and the underlying paragraph as well. Even though almost no ions can flow through the thick myelin sheath, they can flow with ease to the nodes of Ranvier. Therefore, action potential occur only at the nodes. Yet the action potential is conducted from node to node, and this is called saltatory conduction. There is electrical current flow through the surrounding ECF outside the myelin sheath, as well as through the exoplasm inside the axon from the node to node, exciting successive node one after another. There's a nerve impulse jump along the fiber, which is the origin of the term saltatory. And we have already talked about the value of saltatory conduction. First, by causing depolarization pump to jump long interval along the axis of the nerve fiber. This mechanism increases the velocity of nerve transmission in myelinated fiber as much as 5 to 50 fold. Second, saltatory conduction conserves energy for the axon because only the nodes depolarize, allowing perhaps 100 times less loss of iron otherwise be necessary, and therefore requiring little energy expenditure for establishing the sodium and potassium concentration differences across the membrane after a series of nerve impulses. The excellent insulation afforded by the myelin membrane and a 50-fold decrease in membrane capacity to also allow repolarization to occur with little transfer of ions. Heading, the velocity of conduction. Learn the values. The velocity of action potential conduction in nerve fiber vary from as little as 0.25 meters per second in small unmyelinated fiber to as great as 100 meters per second in large myelinated fibers. Now, the next heading is excitation, the process of eliciting the action potential. So, highlight this. Basically, any factor that causes sodium ion to begin to diffuse inward to the membrane in sufficient numbers can set off automatic regenerative opening of the sodium channel. This automatic regenerative opening can result from mechanical disturbance of the membrane, chemical effect on the membrane, or passage of electricity through the membrane. All these approaches are used at different points in the body to elicit nerve or muscle action potential. Mechanical pressure to excite the sensory nerve endings in the skin, chemical neurotransmitters to transmit signals from one neuron to the next in the brain, and electrical current to transmit signals between successive muscle cells in the heart and intestine. Highlight till intestine. To read this blue paragraph, the excitation of the fiber, do not read this, just cross it. And threshold for excitation, acute local potential, no need to read this as well. So this is important, and we have not discussed this in the lecture. Refractory period. After an action potential during which a new stimulus cannot be elicited. So highlight these two paragraphs. A new action potential cannot occur in an excitable fiber as long as the membrane is still depolarized from the preceding action potential. The reason is for this restriction is shortly after the action potential is initiated, the sodium channels become inactivated and no amount of signal applied to these channels at this point will open the inactivation gate. The only condition that will allow them to reopen is for the membrane potential to return to or near the original resting membrane potential level. Then within another small fraction of a second, the inactivation gate, the channels open and a new action potential can be initiated. The period during which a second action potential cannot be elicited, even with a strong stimulus, is called the absolute refractory period. So just highlight till the absolute refractory period. Now, we have already talked about the local anesthesia. If you want to read the text, you can read the text that is written under the heading local anesthetics. So you can read it for your understanding. So this was all about chapter 5. You have to integrate the highlighted text with your slides, and you have to study both of the things together. So I hope this video helps you. Thank you.